Alright, good afternoon, and here we are for the final lesson of CENG 3306 Mechanics of Materials. Alright, so this is going to be lesson 40, and the official title of this lesson in the series is Final Exam Review. Now, this is kind of optimized for a longer semester where I would have a comprehensive final. For students taking in the summer, there's not a comprehensive final, there's just an end of semester third exam, but so some of this material will be useful on our final, and some will not. But anyway, I just wanted to what I'm going to do is I'm going to run through a series of practice problems that are generally useful on a comprehensive final and would be useful to a student taking a comprehensive final, and also for purposes of just sort of summarizing the kind of things we've done throughout the semester. Alright, so I'm just going to work through a series of practice problems detailing and reminding us of some of the highlights from throughout the semester. Okay, so first I wish to review concepts of axial deformation. So this brings us back to columns and really sort of where we started with some early on, some statically indeterminate systems. So let me call this problem, or example 1, or we'll just do problem 1. Axial deformation. And let me double check, we are recording, we are good. Alright. Axial deformation. Well, I guess that'll have to do. Axial deformation. Axial deformation. So if we can recall, in terms of axial deformation, the total deformation will be a combination of axial deformation due to load and axial deformation due to, say, temperature effects. So recall that delta total, or the total change in length, delta total, is equal to delta P plus delta T, where delta P is going to be your axial deformation due to load, and delta T will be the axial deformation due to temperature effects. So delta T is equal to alpha, delta T, delta T like this, and alpha capital delta T, or big delta T, which would be our change in temperature, times the initial length. Or this can be alpha times the original length times T minus the initial temperature, T minus T naught, or T final minus T initial, however you wish to interpret this. And delta P then is equal to P L naught over AE. P L naught over AE. Here. Now, let me calculate, let me look at this, and let's say here, okay. Oh, let's see. So let me show you the system we have. We have a system like this, here. And I'm going to have a series of points. Let's say I have points, let's see, A, B, F, D, C, and E. And each of these are going to have a certain something at it. So I'm going to have some supports here. And let us say that I have some supports here. And let me check up on something really quick. Oh, let's see. Okay. Here. And so we have this here, and then I'm going to have another pin support here. And so I have a pin, and one more pin at D. Another pin at D here. And let us say that this thing has length L, this thing has length L, this is 5 feet, 5 feet, and 10 feet. So I will say that we have, I will give you a few bits of information. Let's see, bits of information. AFCE is a rigid beam. DC or CD and AB are identical rods. Identical rods are identical rods. Let's see here. They have length L is, so these rods, they each have length of 10 feet. Here, let me just see here. Yeah, 10 feet. And they have also, let's say, diameter D. Their diameter is going to be 4 inches. And let's see, what else do we want to know? The yield stress of these things is going to be 50 kSI for the rods, and the modulus of elasticity is 50 kSI. And so the diameter is 4 inches, and from this we'll know the area is 12.56 inches squared. And this thing is going to be under a load of, let's say, a point load on the point E of 30 kips. There's a point load on the end of 30 kips. So we will need to, what we're looking for is, we are looking for the normal stress in each rod. Calculate the normal stress in each rod. Calculate normal stress in each rod. Find, so this is just a case without temperature shifts, it's only with axial force here. The normal force so again, we're going to treat AFCE as a rigid beam. It's not going to deform substantially, it's simply going to rotate. And these two beams here, or these two rods here, these two columns are then going to stretch and or compress. And also, let's see, what else do we have? Do we need anything else? We have the modulus of elasticity, we have that. We're going to assume that they are elastic, however, we will have to check that assumption later. So let's do that. Solution here. So solution. Solution. Alright, so let's look at the free body diagram here. Let us consider a free body diagram of the beam. So we have this beam here, and I'm going to model this as supported by a single pin, but then I'm going to have two forces. I'm going to have F, AB, and I'm going to have FCD, and the 30 kip load here. And the dimensions here are going to be 5 feet, 5 feet, and 10 feet. And I'm going to assume that this thing is going to rotate about the pin. So we always assume that pins cannot move whatsoever. We're treating them as idealized, infinitely rigid supports. So this thing, no matter how much force we apply to this, this will not move at all. So if we apply a vertical load here, this pin will not move downward. It will simply remain as it is, firmly affixed to the ground, and even this rigid beam will simply rotate about the pin. So if I do a balance of moments about F, I'm going to do a balance of moments about F, summation of moments about F. You know what, I like writing these in blue, so I'm going to do that. I'm going to do the summation of moments about F here is equal to 0. And from this, I'll get the following. So 5 feet times FAB, O plus 5 feet times FCD, and then minus 15 feet times 30 kips is equal to 0. And we get the relationship FAB plus FCD is equal to 90 kips. And I'm going to dub this equation 1. I'm going to let this be equation 1 here. Next, let us look at another deformation diagram. Well, let me create a deformation diagram, not a free body diagram. Let me show you what's going to happen. So deformation diagram. In the deformation diagram, I'm going to cut the rods, exposing the internal forces. Cut rods, exposing forces. Exposing internal forces. Exposing internal forces. Alright, so say I have this pin here. The pin at point, what point is that? That's point F. So I'm going to have that pin at F. And I'm going to draw the greatly exaggerated deformation. So this is F again, F. And then the deformed shape, well first I have the original horizontal shape, horizontal position here, and that looks terrible. More like this here. And then I'll have the deformed shape here. The deformed shape here. And then I'm going to have a series of deltas. And I'm going to label these, well first I'm going to label these delta C and delta B, or delta A actually. Delta A because here point A is on the beam. And we have delta E here. Although really ones we're going to need to use are C and A. Delta E. And the distances on here are 5 feet, 5 feet, and 10 feet. 5 feet, 5 feet, and 10 feet. Okay, and then, so I'm going to use the relationship, hey look, these are similar triangles. These here are similar triangles. So I can use the relationship delta A over 5 feet equals delta C over 5 feet equals delta E over 15 feet. Although what we really need is just this portion here. So if we work through that, it's fairly easy to see that the two deformations are going to be equal and opposite really. But the way we constructed it, we can just say delta A is equal to delta C. And this we can call equation 2. Call this one equation 2. So if I work through the equations of axial deformation, and again this is purely load-based deformation, we're not dealing with any temperature effects. So if I say FAC times LAC over A times EAC equals F LCD or FCD over ACD. Let me just say ACD, ECD. Well, ECD here. Basically, what's going to happen, let's see. Well, the L's are the same for each of these. The E's are the same, and the A's are the same. So the forces in them must be equal. We just use the relationship here, and because the two rods are identical, the forces essentially have to be equal. So if we plug these, so we're going to get FAC is equal to FCD. Then we plug into equation 1 here, and we'll find that FAC equals FCD equals 45 kips here. And then, so we found the forces in each one. We have achieved our goal. Well, we've achieved our goal in terms of finding the forces. I guess we still need to find the stresses, and we will need to make sure both of those are underneath or beneath or less than the elastic or less than the yield stress, because we are making this entire assumption. We are making our entire analysis assuming elastic behavior, and if this thing isn't elastic anymore, then we're going to have a problem. If it's beyond the yield stress, then our assumption will no longer be valid. And see earlier videos to see how you would deal with that. Essentially what you do is, once you're past the elastic limit, you simply say the one that is in the plastic zone is going to be simply free deforming past that level, and its actual load will be fixed at the yield load, essentially, for the column. So for normal stress, let's find the normal stress. So first, sigma AB is going to just be equal to FAB over A, and then sigma BCD is equal to FCD over A, which is then equal to, let's say 45 kips over 12.56 inches squared equals 45 kips. These are both the same again because they have the same loads and the same, they're the same rods basically. Inches squared equals 3.58 KSI. So we're going to be well under the yield stress. And also 3.58 KSI. And so both of these are less than or equal to 50 KSI. So yes, our assumption is good, and our assumption is valid, and we are perfectly fine. So by finding these stresses, we have achieved our goal. Alright, next I wish to work through a problem of torsion. Okay, so I'm going to look at elastic and inelastic torque. I'm going to look at elastic and inelastic torque. Alright, so I can ask, so for problem 2, I'm going to have a, let's see, I'm going to look at a combination of elastic and inelastic torque on the same section. So problem 2. Problem 2. Elastic / inelastic torque. Torque. Alright, so I have a section that's going to have a hole in it, and I am going to, let's say that I'm given the following. Oh, I have a, well actually, first of all, let me, I am going to be working with a solid section, so never mind. But let's just review a bit how this works, whether there's a hole in it or not. So, let's see. How can I express this properly? So let's look at the stress-strain diagrams, or the radius for strain and radius for stress for elastic and inelastic torque. So let's say I have a rho. I'm going to put the rho on the x-axis for both of these, and the angular deformation gamma. So let's say I have something like this. This is going to be somewhat of a review from previous times. I cannot draw a circle to save my life, can I? Something like that, and then maybe I could draw something like this. I'll actually get to a problem statement later. I'm just going to review a bit how this works here. And then let's say I want that to be green. So the blue is going to be the black is our outer surface, the blue is our elastic core, and the green is going to be our hole in the middle of it, if we happen to have a hole. So this is going to be CI, the internal radius, or the internal core distance. Rho y is the yield radius, rho y. And let's see, so I can shade this a little bit like this. This again is the elastic core. The green is the hollow hole. Just there's nothing there but air or vacuum or fluid or whatever we have in there. Hole. And the black is going to be our plastic annulus, or outer ring. Annulus. And then the strain diagram is actually just going to go like this. Strain for it doesn't matter whether it's elastic or inelastic. Strain is simply going to be linear. It's just going to increase all the way up. It's just going to go as much as needed here. But although at this point we'll have our gamma yield, and this point we'll have gamma max. And then this is CO, the outer radius. And the relationship is going to be gamma y equals gamma max, each of these over, let's say this is over rho y, and this is over CO. In other words, the yield strain over the yield radius is equal to the max strain divided by the outer radius. So the maximum strain is going to be over at the outer radius, but it's simply going to be a direct proportional relationship. The strain just linearly increases from the core all the way out. Although in reality, since we don't have any material in the inner core, there of course wouldn't be any actual things there, any actual strain or stress there. Okay, let's see. What's next? So now let us review the stress condition for this. Let us review stress. So I've done a strain diagram for inelastic deformation, or inelastic torsion. But what about a stress diagram? What about a stress diagram? So again, I'm going to use the same kind of colors. And again, I cannot draw a circle to save my life. Nice potato. Oh well, it's the end of the semester. It's okay. For some reason. Okay. So there is our plastic annulus, our elastic core, and then the hole in the middle. The hole in the middle. Oh my god, this is terrible. There we go-ish. Okay. So our stress is going to obey a different relationship. It is going to increase linearly, but only up to a certain point. It's going to increase linearly, but only up to a certain point. Actually, let me put that more like, it is going to increase linearly, but only until the end of the elastic zone. Past this point, okay, so we have tau and we have rho here. Once we're out of the elastic core, we have the yield stress the whole way down. So any fibers outside of the elastic core are going to be purely at the elastic limit, or purely at the yield shear stress. So then the relationship is going to be, from this, if we get the forces from this, the total torque, T total, is equal to tau yield, JE, the polar moment of inertia, over rho y, which is then equal to, we can consider the, it's equal to this, plus 2 pi over 3 tau y times C otter to the third minus rho y to the third. So in other words, this is the torque produced by the elastic region, and this is the torque produced in the plastic region. Or, in terms of the J of the elastic, so again, J is going to be the moment of inertia, the polar moment of inertia of only the elastic region. So JE is going to be rho over 2, or sorry, pi over 2, I don't know, apparently don't know my Greek letters today, times rho y, or the yield radius, to the 4th power minus the internal radius of the whole Ci, also to the 4th power. And that's our relationship here. Okay, so now that I've described all this in depth, let me give you let us look at a problem. So I'm going to give us a problem, and this problem is as follows. Given we have a solid circular shaft, so it's going to be a little bit easier because there's no hole, it's just a solid rigid shaft. Given a solid, sorry, not a solid rigid shaft, a solid circular shaft. Rigid would imply a rigid body. Solid circular shaft, and tau yield is going to be 20 ksi, and gamma yield is going to be 0.002 radians. And finally, R is 3 inches. The outer radius is 3 inches. The actual radius of this thing is 3 inches. And so we just know from this sample that the yield radius is going to be 0.002 radians. Or sorry, I can't say that right. Not the yield radius, the yield shear stress, the yield strain. Apparently I do not know mechanics of materials today. Gamma y is the yield strain. This would be a material property. So the yield shear strain will be 0.002 radians. We also know that the material has a yield shear stress of 20 ksi, and this shaft has a radius of 3 inches. These are things we could logically know before we actually did any analysis. These are both material properties, and this is just something, well, we have something of a certain size, we know its dimension. So I want to say find torque if gamma max is 0.0025 radians. Alright, solution. 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 First, we need to find the elastic core radius. Find elastic core radius. Now, based on, we're going to find it based off of this fraction here, or this proportion here. So, let's see, solving that for rho y. Rho y is equal to gamma y, CO over gamma max, equals 0.002 radians times 3 inches over 0.0025 radians, and this is going to equal 2.4 inches. So most of the radius of the cross-section is actually going to be elastic, but the outer 0.6 inches is going to be in the plastic zone. So let me find the elastic polar moment of inertia, JE. So let me label this section of the notes. Elastic polar moment of inertia, JE, of inertia, JE, J subscript E, and JE, we're just going to use the formula from before. Well, we know that JE equals pi over 2 times rho y to the 4th power minus c internal to the 4th power. However, this is a solid shaft, it's not hollow, so this just goes away to 0. In other words, we can say that this will produce, not yield stress. This will produce JE equals pi over 2 times 2.4 inches to the 4th power, which equals 52.11 inches to the 4. 52.11 inches to the 4th power. Inches to the 4th power. And then finally, total torque. Let us combine all this together to find the total torque. Total torque. In red, I'm going to do this. TT, total torque, is tau y JE over rho y plus 2 pi over 3 tau y times c outer to the 3rd minus rho y to the 3rd here. And the outer radius again is 3 inches. And we will find, if we just plug all this stuff in, we will find that the total torque is equal to 986.2 kip inches. 986.2 kip inches. Total torque. And that concludes problem 2. Alright, problem 3. Here. And then I'll give a few notes on boundary conditions. This is so I'm going to have 3 problems, and then I'm going to have one more problem, or not one more problem, but one more thing after this where I discuss boundary conditions for beams, and that'll probably be the most useful part of this lecture for students taking the class this semester. Alright, so the next example problem is going to be over let's see, actually axial temperature deformation. So let's look at this, problem 3. Temperature-induced axial deformation. Temperature axial deformation. Deformation. So A, determine the normal stress. Oh, let me actually draw the problem out first, that would help. So let us say we have a system like this. I have 2 rigid supports, or rigid walls here and here. And then I have a beam that it will be free to expand or contract. And it has an initial length of 30 inches. So this is the initial length, which is 30 inches. 30 inches, undeformed length. And the initial gap, we have a very small initial gap, but it's greatly exaggerated here. The initial gap is 0.002 inches. So then, E is 29,000, and I'm also told that the modulus elasticity of this is 29,000 KSI. 29,000 KSI. And the coefficient of thermal expansion, alpha T, is 6.6 times 10 to the negative 6 inches per inch degree Fahrenheit. In other words, strain per degree Fahrenheit. And so I'm just going to calculate the stress for a series of cases. So A, determine normal stress. The normal stress due to delta T is equal to negative 50 degrees Fahrenheit. Okay, so let's see here. Well, I'm going to go back to the formula that we saw previously. Delta total is equal to delta T plus delta P. However, let's see what this says. Let's see if we're going to have a problem with this. You might be able to see where this is going already, and if so, that's good. Delta T equals alpha times T minus T naught times L naught equals 6.6 times 10 to the negative 6 inches per inch per degree Fahrenheit times negative 50 degrees. It's getting colder, which means it should be contracting, so we're probably not going to have a problem. The only time a temperature decrease will cause a stress is if this thing is, say, fixed here. If this were glued down here, then it would cause a tensile stress in the material. Equals negative 0.0099 inches. Well, so what does this mean? Well, let's interpret this. So we have the fixed support here. So this is a case that we can't just rely on the mathematics. We do have to interpret it. This is the initial length. However, the deformed length is actually going to be even shorter. So the gap is actually going to grow. So that's the deformed length. And the difference between the original length and the deformed length here, this is going to be 0.0099 inches. And so then I can work through the stress equation, or the deformation equation. You'll see delta P is PL over AE equals, well, this is the deformation due to load. Delta P equals PL over AE. So we got the delta T, and that's this, and the delta P is just PL over AE, which is sigma L over E, but however, this must be 0 and this must be 0. 0, 0, so just sigma is equal to 0. There is nothing constraining this thing's deformation, so it's just going to have 0 axial stress. Next, I am going to determine sigma. Determine sigma due to delta T equals 70 degrees Fahrenheit. If delta T is 70 degrees Fahrenheit. So this actually might cause some issues. Well, let's find the deformation due to delta T if the thing is just completely free to expand. So delta T equals 6.6 times 10 to the negative 6 inches per inch per degree Fahrenheit times 70 degrees Fahrenheit, oh, not 70 degrees Fahrenheit, 70 degrees Fahrenheit times 30 inches, which equals 0.0139 inches. And then, so let's look at this. We have the initial length, there, the initial gap, which is going to be, the initial gap is 0.002 inches. The initial gap that we saw earlier was 0.002 inches. However, how does this thing actually want to deform? Well, it needs more space than that. It needs, if it were to have its way, it would deform out much greater distance. If it were completely unconstrained, and let me make clear that this is a rigid wall here with my hash lines here. If it had the option, if it had its way, if the temperature effects had their way, this thing would be deformed outward a full 0.0139 inches. 0.0139 inches here. But this can't be. This cannot be. We are going up against an immovable object. We will not be able to expand that far. So instead, it's going to be forced backward. And in order to calculate that, imagine an axial force, an external axial force, coming along and forcing this expanded rod back to a displaced length of 0.002 inches. So we're going to go back to our delta total equals delta t plus delta p equation. So we're going to go back to our delta total equals delta t plus delta p, and work through the equations here. 0.002 inches equals 0.002 inches, 0.0139 inches plus sigma times 30 inches over 29,000 KSI. And we will find that sigma is equal to negative 11.47 KSI, or sigma is 11.47 KSI in compression. 11 point, so quite a bit of temperature-induced load. 11.47 KSI, that's a lot of load, just from temperature. Okay, and finally, I would like to just do a bit of a review of boundary conditions. Beam deflection boundary conditions, just sort of a bit of a cheat sheet that you might look at for the exam. This will be very useful for students watching this semester. Beam deflection boundary conditions. So I want to look at a couple cases here. Oh, let's see. What else can we do? Well, let's say we have the two big ones are our fixed and our simply supported case. So we have I'm going to have a fixed beam first with a P here, and let me again use some hashed lines here to show that this is fixed. Make very clear this is a fixed support. And X is, as always, measured from the left, increasing to the right. Well, we have a few things. One, this is X equals 0, but the deflection is also going to be equal to 0. The vertical deflection is equal to 0, and the rotation, or the slope of the beam at that location, must be equal to 0. Next, if we have a pin-pin or a simply supported roller pin system, it would be the same for either one. Here, something like this, something like this, and again the slope of this, or the shape of this, would be something like this, where we start off horizontal with a 0 slope and we gradually increase our slope. Here we're going to have a slope right from the get-go. It's going to be just a smiley face kind of shape, assuming we have a load right in the middle. P, and we could have a few boundary conditions here. We could have, again, x increasing from the left, but here we know that y equals 0, and also y at x equal L is also equal to 0. However, our angle of rotation, theta here is n equal to 0, and theta here is n equal to 0. Now, what's next? Let's see. What if we had something more complicated? What if we had finally, what if we had something like this? What if we had a beam that had a load at a particular point, at a special location? What if we had a load 1/3 the way across? 1/3 of the way across. Here. We had a P here, and then maybe a load. So if you do know something about the load, you can develop more boundary conditions based upon the peculiarities of that load. That looks a bit bad. So say this is x equal L over 3, and say this x is 2L over 3. So the length of this portion is 2L over 3, and this is L over 3. And let's see. So let's see. What do we know? Well, let's say I had I would have two equations here. I would have, well, first let's look at the deflected shape here. It would not be symmetric. The lowest point in the beam would be directly underneath the point load. It's going to be something like, oh my goodness, didn't want to go to the next page. Something kind of like this. This is kind of exaggerated, sort of like a swoosh, like that. So I would have a y1, we're going to have a y1 as a function of x, and a theta1 as a function of x. So we'd have a piecewise deflection and rotation curve. And x, then x1 is this is for x is less than L over 3. And then we'd have a second one here of y2 of x. So this is going to be two different equations because of the discontinuity. And theta2 of x for x is greater than or equal to L over 3. So what about some boundary conditions? Well, what about some boundary conditions? Boundary conditions? Well, we're going to need some more boundary conditions than just the two here, just the one on the left and the right. But we can use the, well, you'll see. y1 at x equals 0 must be equal to 0. That makes sense. Actually, let me do that in blue, because I'm going to do all these in blue. y1 at x equals 0 is going to be equal to 0. And we also know, because of the pin support, or in this case the roller, they both exhibit the same vertical behavior. y2 at x equal L is also equal to 0. Then we could say y1 at x equals L over 3. And we talked about this yesterday. Oh, let me put this on the other side, sorry. Let me go back to blue. we need more boundary conditions than just these two. So the y1, and we get them from compatibility, y1 at x equals L over 3 is equal to y2 at x equals L over 3. y2 at x equals L over 3 and then theta 1 at x equals L over 3 is equal to theta 2 at x equals L over 3 equals theta 2 at x equals L over 3. In other words, it's the same beam, it is continuous, so everything, as long as it's a physical system, the slopes and the vertical deflections must match up at the meeting point. So again, slopes and deflections must match at merge point. Merge point. At the merge point. And so what you'll have here then, for this kind of problem, you will have four unknowns, four unknown constants, and four boundary conditions, and you can solve for all of them. And so those are just a few quick notes for final exams that may be useful in this or future semesters. Again, if you are watching this semester, the final is not comprehensive, but for future semesters, for future long semesters, they will, of course, will be. Alright, so with this ends my lecture series for CENG 3-6. For those students watching these this semester, it has been a pleasure being your instructor. I've met a few of you in person, even though this is an online class, but I do appreciate all of you putting up with all of my foibles and random stories and things like that, and wandering tales. So I hope you enjoyed this lecture series. I hope you learned quite a bit. If you have any questions before the final exam, please let me know. It has been a pleasure to be your instructor this semester, and I hope to see some of you in future courses to come. Hope you've all learned something. It has been a privilege and a pleasure, and I wish all of you good luck on the upcoming exam, and thank you as always.